balanced equation. So we have 1.5 times 790 and then divided by 2. Comes out to 590. Is it? Yeah, to two significant figures. 590 kilojoules. And lastly, for part C, if we have 150 grams of oxygen forming, how much heat will be required? Again, two significant figures in our answer. We need to first convert this to moles so we can get the mole ratio. 1 mole of oxygen is going to be 32.00 grams. And we see that for every 790 kilojoules of heat that's absorbed, there's going to be 3 moles of O2. So 150 divided by 32 times 790 divided by 3 to two significant figures is 1,200 kilojoules of heat is required.
Which element in each of the following pairs has more non-metallic character? Non-metallic character usually relates to its ability to hold an electron tighter. A. Boron or aluminum? Boron is higher in the group, so it has more non-metallic character. B. Germanium or bromine? Germanium or bromine? Bromine has a higher group number, it's halogen, so it's more non-metallic than germanium. C. Indium or selenium? Indium and selenium. First, we look at the group number. Selenium has a higher group number, that's chalcogen. So selenium has a more non-metallic character than indium. D. Chlorine or tellurium? Chlorine has a higher group number, it's halogen, it's more non-metallic than tellurium. And besides, it's also up in the group, which also enforces this answer. So, chlorine.
So a method of producing phosphine PH3 from elemental phosphorus, P4, involves heating P4 with water to produce PH3 and phosphoric acid. We're asked to balance this equation, and this one happens to be a pretty tricky one to balance, just the way that the elements are broken apart. And the one that I see is on the right-hand side, I see oxygen with 4, and then I see the oxygen with 1. So that means that in order to make the oxygen balance, and then of course we have the hydrogens, we're going to need multiples of 4. And since we have 3 hydrogen and 3 hydrogen, I think the best number to start with is going to be 12. So if we put 12 there, then the phosphorus is the last one we're going to balance. So if I put a 12, then that means that I need to come up with a way to get 24 hydrogen on the right-hand side. So let me put the 12 here, so that would be a 3 would make the 12 oxygen. And then that gives me 9 hydrogen on that side. So now I need to be able to come up with 24 hydrogen. Well, if I have 9, if I come up with 15, that's going to give me 24, and I need a multiple of 3. So I'm going to put a 5 there. And then that gives me now, I have 12 oxygen on this side. I have 12 oxygen on this side. For my hydrogen, I have 9 plus 15 is 24 hydrogen. And I have 24 hydrogen over here. So that looks pretty good. So now we're going to go to the phosphorus. So I have 3 phosphorus from the phosphoric acid and 5 phosphorus from the pH 3, which gives me 8. So that means we're going to put a 2 here. So that would be my balanced chemical equation. So I hope that you found that helpful. Have a great day.
Okay, so this will be a review of how to determine the hydrogen ion or proton concentration, this H plus here, in a solution at a given pH. So you can see the mathematical relationship that I have written here. Just a quick note on this. So I have it written as the concentration of H plus. Sometimes you'll see this equation written as the H3O plus, the hydronium ion. For the purposes of these types of calculations, they mean the same thing. So you notice that I have this written in brackets here. Just a quick reminder, whenever we use these brackets, we're talking about the concentration of these species in molar or moles per liter. So if we look at this equation, it's expressed in terms of the pH equals. So we want to essentially rearrange this equation so that we can get the concentration of the hydrogen ion by itself if we want to determine this value. So we can first divide each side of this equation by -1. This will get rid of that negative sign in front of the log value here. So if we have negative pH equals the log of the concentration of the hydrogen ions or the concentration of protons in solution. So we often just write this as the log of the value. We're talking about logarithm to the base 10. Usually if that's not explicitly written, that's implied. So we can do sort of an algebraic transformation in order to get this concentration value by itself. So if we take the base of the log, which is a base 10, and we raise it to the power on the left side of the solution, which is the negative pH, we can set this equal to the concentration of the hydrogen ions. So this is also sometimes referred to as taking the anti-log. So if we have the concentration of the hydrogen ions is equal to the base of the logarithm, which is 10, raised to the negative pH power. Okay, so now that we've rearranged the expression, we can basically just plug in a value for the pH, put it in the calculator, and then calculate the concentration of hydrogen ions in solution. So we can do a couple examples to show this. So let's start off with doing where the pH is equal to 8.34. So if we have a pH of 8.34, we can plug that in as the exponent in the solution or in the equation here. So if we want to know the hydrogen ion concentration. We know that we can solve this by doing 10 to the minus 8.34 power. It's just important to remember when you're doing these calculations that you always remember this negative sign in the exponent here. So if you were to put this in the calculator, go ahead and solve that. So it'll come out to 4.6 times 10 to the negative 9. So these values are pretty much always going to be expressed in scientific notation. So that way we're not writing this out to too many decimal points.